Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz, and we've taken today's webinar out on the road, and so we're not in our typical space for our webinars. So I hope you enjoy our topic for today. We're going to be looking at Torque 101, a guide to the fundamentals of torque control. And so this is going to be a very intro to torque type of session. So if you do have some knowledge in this area, it may be a bit remedial or a bit of a back to basics type of discussion. But what we're going to look at is we're going to be talking about what is torque, why we use it. We'll go over some torque terminology, how torque is measured, and how that equipment works. And then we'll look at different types of torque application tools that are available for us to use to create and generate torque. So without any further ado, let's go ahead and jump right into today's presentation. And so first off, what is torque? Now, the classic definition of torque is we're going to be measuring the turning or twisting force around a axis point, and that is the classic definition of torque. Now, you may hear torque being advertised for vehicles producing so many foot-pounds of torque, or an electric motor that may have a torque rating of a certain amount of torque. And this is all of that twisting force that is being measured and what it actually produces. When it comes to fastening, torque is a little bit different than that in that context of applying torque to a fastener. And what we're really trying to achieve in the end is generating clamp force. And the clamp force is when we put two pieces together, and the amount of pressure that is holding those pieces together is done through the use of torque, which is creating tension on the fastener. Now, clamp force, the definition for that is going to be a measurement of the generated tension that is indirectly controlled by the applied torque to a fastener. And again, as I demonstrated, we're basically wanting these two pieces not to move, to come apart, which is what we're trying to achieve by using fasteners to do that. Now, this animation will help to explain kind of what we're looking at. With a bolt and a nut and our threaded fastener. As we apply our torque or our twisting force to the nut, that's going to stretch the bolt, giving us our bolt tension there, causing the two pieces that we're trying to come together. That is the clamp force, what we're trying to achieve. And so in essence, what we're looking at is we're using torque to create tension in the fastener, and that is going to produce the clamp force that we need. And so that is, in the end, what we're trying to get to is the correct clamp force with the correct torque, creating the right amount of tension that is needed on that fastener. Now, when we look at fasteners, each of them have what is called a tensile strength, meaning that we can stretch those fasteners, and if we remove the tension from that, it will come back to its original size. And tensile strength is measured by how far we can take that fastener to a certain point before it will break. And in the world of fasteners, the video clip there that we're showing is not necessarily a fastener, but it does give you that same representation. We can stretch this to a certain point with a normal fastener. If we release that tension, it will go back to its original length. However, if we take the fastener stretch too far, we'll get to a point where it will begin to deform and then finally break. The point at which is the point of no return in there is called the yield point. And basically we've taken that fastener to a point at which it will no longer return to its elastic region or its ability to return to its original size. And so often fasteners are referred to as almost like a rubber band. You can stretch that rubber band. If you remove the tension, the rubber band will go back to its original shape. However, if you take it past its yield point, the rubber band may break or it will return to its normal size. And so typically a fastener is going to have what is called a proof load rating, which is about 85 to 95% of the yield point. And so if we stay within that particular amount of tension on that fastener, it is going to stay within its elastic region. And we see torque failures sometimes when we push a fastener, it gets over torqued, or we apply too much torque to it and it moves the fastener close to the yield point, and then any type of shock or vibration can cause that fastener to break because it is at or past the yield point of that fastener. So that is typically where we want to be as it relates to the fasteners, but that is how tension is working within the actual fastener. And so in this example, you see two fasteners that one is able to return to its original size. The one on the right there is a little bit longer because it has been deformed and it will no longer return back to its original size. It has been moved past the yield point for that particular fastener. Now, when we're talking about measuring torque, as it relates to general terms, it is going to be a calculation based off of force and distance. And so if we have a wrench here and we are applying load to that fastener, if we put 2 pounds of force on that wrench at a 1 foot distance, we have created 2 foot-pounds of torque. Again, so it's distance times the force. Now, if we extend our wrench out to 2 feet, we use that same 2 pounds of force. We now increased our torque to 4 foot-pounds. 2 times 2 is 4. And so that is the rough definition of how we measure torque. It's going to be the amount of distance that is used around the access point with how much force is being delivered at the end of that distance. Now, we also use torque analyzers to measure the amount of torque that a tool could be producing. And that is done by taking an analog signal and we convert it to a digital signal. And that's done through the use of a strain gauge. And so if we put a wrench into a torque analyzer, what we're basically doing is we are adding a kind of a tensional or torsional force to a stock that has a strain gauge on it. And we're now converting the digital or the analog signal to a digital signal. And the strain gauge does that very nicely. This is a little electrified circuit that is less than a postage stamp size stamp. And this is laminated to a stock. And that electrified circuit, as there is tension or torsion on the stock itself, it's going to produce a different electrical signal output as that torsion happens. And so in this animation, it kind of gives you maybe a little bit more of an exaggerated view of it, but we have our strain gauge laminated to our stock. And then as torsion happens to that stock, the signal that comes out of that electrified circuit is different at different torsional ranges. And so we use the torque analyzer and the strain gauge to give us a signal of what the amount of torque that was generated when that torsion happens. And that is all culminated during the actual calibration of the torque sensor or the strain gauge with the use of dead weights. And so we have our force, which is our weights. We have them out at a certain distance. In this example, it looks like that's a 2-foot wheel or 2-foot segment arm, and we're hanging weights. So whatever calculation it is based off of the amount of weight multiplied by 2, that would give us our foot-pounds. And so we do this at different points throughout the range of the sensor, and that then is all calculated through the processor of giving us our torque output for the actual reading on the torque analyzer. So that's how the torque analyzer is actually reading the torque that's being generated by the tool that we're testing. Is we are adding torsion to the stock, which is changing the electrical signal from the strain gauge, which was calibrated through the use of the segment arms and dead weights. And so our screwdriver here, our torque screwdriver, gets calibrated on a torque analyzer. That torque analyzer is calibrated through the use of segment arms and dead weights. And this is all part of a measurement traceability that we have. And so we know that the screwdriver, we could trace that all the way back to the dead weights. If you look at a calibration certificate, the calibration certificate will have whichever analyzer it was calibrated on. That analyzer, if we look at the calibration cert for that, it's going to tell us what the dead weights were, and so on. So we have all of that traceability. We can be assured that the screwdriver can be traced back to the dead weights that were used to calibrate the torque sensor. Now, when we look at units of measurement, we started with our imperial units, which are our distance, which is foot pounds and inches. And then we have the different scales for that. So we have foot pounds, we have inch pounds, and then we have inch ounces. And now there are 16 inch ounces in 1 inch pound, and there are 12 inch pounds in 1 foot pound, and so on. And that works throughout the unit, depending on which type of unit you want. Those all will produce the same value, but just a different unit if we are doing the measuring of that. Now, there are different units of measurement. If we look at the international standard, we have Newton meters, Newton centimeters, Newton millimeters. And so this is the international standard. And just to kind of give you an idea of what this is, if we have a lever arm and that lever arm is 1 meter in length, we will put a 1 Newton at the end of that, which is equal to 0.2248 pounds, which is the amount of force needed to accelerate 1 gram of mass at the rate of 1 meter per second squared. So we are putting basically this unit of weight at 1 meter, and that is what 1 Newton meter looks like. Now, there also is a metric standard, which is our grams and meters. So often people will think that the international standard or Newton meters is a metric measurement. It is, as part of it, it has a metric length to it, but it does not have a metric force to it. And so in this case, the metric standard uses grams force or kilogram force. And those could be in either centimeters or meters. So that is the difference between the international standard and the metric standard, would be the use of both units in a metric type of standard. So all of these are interchangeable, or not interchangeable, but they all will produce whatever reading that you might need. If you do have a need to do any type of torque conversion from our website. Just about on any page of that site, we have a link to our conversion calculator. You can just enter in the value that you have, hit convert, and it will show you what that value is in all of the different units of measurement that we have on there. So that is a handy tool if you so need that. So now let's take a look at some torque tools. And not all torque tools will use a lever arm and a force, but we use another way to create a repeatable type of force that we can measure and use. And let's first take a look at torque screwdrivers. Now, the Mountz screwdrivers, nearly 100% of them, all use a spring and spring compression to create a certain torque value for a given output of torque. Now, this is accomplished by the use of a cam mechanism within the internal body of the screwdriver. So we have three ball bearings that sit inside a cam housing. And as we rotate the tool, those ball bearings will push in on a single ball bearing, which compresses the spring. And so depending on the cam configuration, that is going to compress that spring to a certain point, and then once the cam or the tool cams over, it releases that pressure, and so we're getting a repeatable amount of torque during that particular application. Now, the spring itself can be adjusted to either provide more torque or less torque, depending on the output that is needed. That screwdriver then is put onto a torque analyzer and verified and checked. And that is how a torque screwdriver will use a spring to create the amount of torque that's needed for a given application. Now, there are other different types of torque repeatability type of tools, but in most cases, you're going to see this type of spring compression across all torque screwdriver type of lines. It's just how that spring is compressed that makes differences between different manufacturers and different types of tools. Now, when we're looking at torque wrenches, the same principle applies. We typically will use a spring to go ahead and create the amount of force that we need to signal when that force has been achieved. And so if we look at the wrenches that we have here on the screen, we've got a cam over wrench, a breakover wrench, a click style wrench, and then also a digital wrench. Now, all of these use a spring except for the digital wrench, which uses a sensor to be able to capture the amount of force that's happening. So in the other three cases, we have a cam over style of wrench, which works very much like a screwdriver. There's a cam mechanism in there, and then as the tool is being used, that cam will slip, and then we know we've hit a certain amount of torque, and then the tool will reset itself. And so that is a cam over style wrench. This is a really good wrench to use in highly critical torque applications because it does not allow there to be any additional over torque that would happen when that wrench is being used, because it can only go and provide as much torque as the cam would allow. So again, a very, very good wrench for critical type of torque applications where we don't want to push a fastener to the yield point where we could see possible failure from that particular fastening. The next wrench is going to be a breakover style wrench. And so this again will use a spring, and what will happen is when that spring gets to a certain point, the wrench will break over, and so we get a real clear signal that we've reached torque when that head begins to break, and that is how the spring is being managed with that particular style. The click wrench, which is by far the most popular and most used wrench in the world. This will basically, as we pull that wrench, it will click. It will give you a little bit of a movement to notify you that torque has been achieved. However, it does not guarantee that you're going to add additional torque to that, because once the wrench clicks, if you keep pulling on it, you're adding additional torque to the assembly. So the click wrench is a very operator dependent type of tool. If the operator can pull that wrench slowly and evenly and wait for the click and then release it, those tools work fantastic. However, if you see an operator out on the line that will double click or sometimes triple click, going really fast, we're adding a tremendous amount of torque, sometimes 2 to 3 times the amount of torque that particular application is calling for. And so again, the click wrench is a very economical wrench. It's very easy to use, but it's very easy to misuse as well. Now, the digital wrench will signal when torque is achieved. So you can set a preset value in there and you pull that until you hear the beep of the wrench and then release it. Now, there's no way to stop you from pulling too far on a digital wrench. But again, it's going to alert you when torque has been achieved for what you are looking for. These wrenches all work off of the distance times force ratio. The only one that doesn't is going to be the cam over style wrench, because the fulcrum point on this particular tool is at the end of the wrench. And so we can hold it anywhere we want up and down the handle. It's always going to produce the same amount of torque. If we were to hold it at 2 feet or 1 foot, it's always going to slip and it will always produce that same amount of torque. Now that's going to be different for the breakover wrench and the click wrench, because our fulcrum point is down inside of the tool, not at the end. It changes that ratio that happens with our distance times force. And so if we were to grab a click wrench and we weren't using it on the handle, or were the line of that, there's usually a mark on there that's telling you where to pull from. If we move closer to the head with that, we're going to be adding more torque. And then if we put an extension on the end of the tool and pull from there, we're actually producing less torque. And so that's another thing to consider when looking at torque wrenches. We want to make sure that we're pulling it from the right spot. Again, because the fulcrum point is inside of the tool, not at the very end of that. Although there is torque output at the end, it's not the fulcrum point for those particular tools. Next is going to be, if we move into an electric style of tools, and there are several different styles of these. There are brush motors, there are brushless motors, there are ones that have special features that will clutch out twice, some that have a special reverse feature in them. But these types of an electric tools, again, are controlled by a spring mechanism or a spring clutch in them. And depending on how much we compress that spring to begin with, is going to give us our torque output. So a torque screwdriver, an electric torque screwdriver, in this case, a clutch tool, is going to have a certain range that it can meet based off of the spring that is in the clutch mechanism. Now, these tools do have reference marks on the nose cone. And so as we dial that nose cone up or down, so if we dial it up towards the body, we're going to be increasing the torque. If we loosen it and move that nose cone away, we are being able to decrease the torque that output of that. But depending on the spring that we have in there, that is going to give us our torque output for that particular tool. So that tool will run down as we squeeze the trigger. The clutch mechanism will engage and shut off the tool, and that will be our torque output. And these tools can be put into the torque analyzer as well, and we can measure what the torque output they are generating. We also use a joint simulator or a rundown adapter within the torque analyzer to help simulate that actual motor running during the assembly process. So these types of tools, although there are a lot of different types that are more specialized for different areas of the actual assembly, they all function the same way using a spring clutch type of mechanism in there. Now there's another style of electric tool, which is a DC controlled type of tool. Now these are basically a computerized tool that gives us the ability to shut the tool off based off of either a sensor that is inside of the tool, or we may take a current draw from the system and equate that to a certain torque value. But these tools are extremely advanced, and they give us a lot of control over what the actual process is. So we can control how the tool operates. We also get a lot of information back what happened during the actual rundown. And the current trend in the industry that has been moving this way for a number of years now is being able to capture all of that fastening data that happens, store that data, include it into an MES system or other type of data collection feature. And so you have that ability to look back at a particular job, a particular part, and you have evidence of what happened during that particular rundown. And so the DC tool is a more expensive type of application, but more and more it does give us that ability to have a lot of control, a lot of flexibility, and a lot of traceability as it relates to fastening. And these go from very, very low inch ounce settings up to up to 50 Newton meters in most cases for these types of tools with different orientations, such as the right angle, inline, or pistol grip style of tool. The another style of tool that also works off of either a spring clutch mechanism or we also have a hydraulic version are going to be tools that utilize pneumatics. So you may have an inline air tool. Again, it works off of the same type of scenario where we're taking a spring in a clutch mechanism, and as that spring engages the clutch, it will simply shut off. And there are different orientations. The big advantage to using a pneumatic style of tool versus an electric tool is that you can go to a much higher torque range that you may need for those particular applications. And in some cases, if we use what would be considered a hydraulic pulse tool, it uses a special hydraulic clutch mechanism that's very similar to an impact style of tool where it will hammer on a fastener. We can get very, very high torque values without any or much reaction to when the tool shuts off. And so the hydraulic pulse tool is a good option for those types of applications. However, their accuracy is not as good as a pneumatic clutch tool. And the pneumatic clutch tool isn't quite as accurate as an electric clutch tool, and an electric clutch tool isn't quite as accurate as a DC control tool. So that's kind of the progression as it relates to different styles of torque tools in the way that they relate to accuracy. We also have for very, very high torque type of applications. So we may need anywhere from 800 to 50,000 foot-pounds of torque. We can do that through the use of a torque multiplier. And that's basically a gearbox that has a certain gear ratio that allows us to put an input in, and it's going to give us a much greater output out. And so these can be computer based controlled to give us a certain precise input and then give us the output needed throughout that gearbox. And that gearbox could be set to a 4-to-1 ratio, 8-to-1, 16-to-1, 32-to-1, depending on the type of torque that would be needed. And so if these come in an electric type of version, they also come in a pneumatic style of version, and also they come in with a manual input type of version as well. And so if you have in this case, maybe it might be an 8-to-1 multiplier. If we have a torque wrench, just a simple standard torque wrench, and we set that to 100 foot-pounds, as we use this multiplier, it's going to deliver 800 foot-pounds at the end of the socket there. And so we're using minimal amount of input, and we're getting whatever value we're looking to achieve at the end of that use of the torque multiplier. So different ways to achieve the same thing, which is we're trying to use torque to create tension in their fastener, which is trying to get us to the correct clamp force that we need to be able to hold our parts together, which is what we're truly trying to achieve in the end. So that is going to conclude our basic fundamentals of torque. I know we ran through a lot of different information in a lot of different scenarios, and in any one of these areas we can extrapolate that, and we do have quite a bit of information in some of our other webinars that can get a little bit more into the depths of what those certain areas are. So feel free to go ahead and look at our different catalog of webinars, and you probably can find the topic that might get you a little bit more information about that specific area. Now, if you'd like a little bit more information, or you want to maybe take a look at how it may be looking for your particular application, feel free to contact us, and we will certainly be glad to help you take a look at that. And with that, that's going to conclude today's presentation. And so we'll move to our questions and answer section. And so today, let's see, Chris, do we have any questions?
Hello, Dave. One question we had was, how can you detect a joint relaxation event in a torque application?
So if you have a very soft type of joint, what you can use would be a rotary type sensor with a torque analyzer, and you can measure the amount of torque that's being applied to that particular fastener, and then you can come back and audit that and see exactly where that fastener is. But oftentimes you'll see in a really soft type of gaskety joint, you may use a tool that, as I mentioned, some of our electric tools that have a double clutch mode, which will allow that soft joint to compress, and then it will immediately relax, and then it will compress it again to get that additional torque there. Because of the amount of compression that may happen during the relaxation process, you're not getting the item to fully seat. You could also use a DC type of control tool where you can run it to a certain torque value. You can have it use a special mode that will allow you then again to retorque it. You could add turn to it. But if you want to measure it, you would do that with the use of a torque analyzer and a rotary type of sensor that would allow you to test the tool as you're running it down to see what the actual torque output is when the tool shuts off. And then you can audit that after the fact as well, and develop some type of correlation between what the actual torque you're getting if you're only doing it that one particular time.
All right. Well, another question we had, Dave, was, does like a nylon lock or a patch impact torque applications?
It certainly does. Now, remember when we're talking about the torque that we're applying, we're really looking at the amount of um, torque that we will get signal. So, in our case, if we're trying to achieve clamp force or get the right clamp force, how much prevailing torque happens is going to affect that final clamp force. So it's not going to change the torque that the tool is delivering. It is going to change the amount of tension that we see on that fastener. And so if we have a torque specification, just to make it easy, it's at 10 inch pounds. And we know that 10 inch pounds is going to get us the correct tension that we need for the correct clamp force that we need. But if we put a nylon lock on that fastener, some of the torque that's being seen by that fastener is being taken up by that lock. And so if it takes 5 inch pounds just to turn that fastener through the nylon lock, if the wrench will hit torque at 10 inch pounds, we really only have 5 inch pounds of generated torque or tension on that fastener. And so for us to get 10 inch pounds of tension on that fastener, we need to make account for that prevailing torque. And so if we do some measurement on that and we calculate that, okay, so for this application, we actually need to set the tool to 15 inch pounds to get 10 inch pounds of torque on the fastener to create the correct amount of tension. And so that type of prevailing torque is something that needs to be accounted for. And so we do have ways to do that where we can measure it. We have specialized tooling that will go ahead and account for that and add additional torque to the fastener based off of what that prevailing torque is. And so if you need more information for that, we can certainly get that.
All right, Dave. Another question we had was, can you speak to why angle measurement isn't a calibrated function?
So again, when we're looking at fastening and the use of angle with there, what we're doing with the angle kind of can be correlated to the prevailing torque. Is we're basically removing friction influencing the amount of torque that is being generated. And so when we look at torque, it is a function of friction as we're applying load to the particular tool. It is seeing some friction that's happening with that fastener. There's bearing frictions on the head. We're looking at friction that is being generated by the threads of the fastener. And so by using an angle type of tightening process, we're eliminating the frictional element from that. And so if we know that from the point at which the fastener gets seated or makes contact with the surface, we know that if we turn that fastener 90 degrees of rotation, we're always going to get that same amount of stretch we're looking for, that same amount of clamp force that we need, regardless of what the torque is, because the frictional forces are going to be different based off of a number of different items. It could be if that fastener is supposed to be lubricated, if there's not lubrication, because if there is lubrication added, it's going to make it much easier to turn, and we're not going to have as much friction. That friction won't show up in the final torque. It could possibly lead to more stretch in that fastener. And so angle tightening is a way of trying to get to the correct clamp force without necessarily using torque.
All right, Dave. Another question we had is, if we're using like a flexible adapter on the end of a torque screwdriver, will it have the same effect as like torque when you're using like an extension on a click wrench or any type of wrench?
So if you're using an adapter on a tool that keeps the drive in the same orientation. So you're changing from a quarter-inch drive to a 3/8 inch drive, and you're using that type of an adapter. That's not going to have any effect on the output unless you do multiple ones of those, and then you're going to have some frictional loss that happens during the transmission of those adapters. But in general, you're not going to see that much difference, if any, in those particular setups. What would be different would be if you put an open end wrench or a spanner on the end of a click wrench, or a breakover wrench, or even a cam over wrench. That is going to change the final torque output, because we're changing the torque, or the force times distance formula. And so that needs to be accounted for with the extension that is put on the end of the tool. Again, so if you're adding a spanner to a drive of a particular torque wrench, then that needs to be, that calculation needs to be done, because it will change the final torque output.
All right. If you're using like a split or a star washer, will it impact torque on a fastening application?
It um it could, based off of the again, any type of difference in the frictional forces that happen. But if, in most cases, that is going to be kind of a constant type. So as long as that is part of the calculation in the original application, then it should be taken in account for. But if you were to use a wrong washer in a different application where it's not being spec'd for, or not being accounted for, then it will possibly have a different torque output for sure.
All right, Dave. A quick follow up on the angle question. For like a torque and angle measurement wrench, why isn't the angle element calibrated on that wrench?
It's most likely because of the mechanism that is being used to calculate the angle. So the gyro that might be inside of that tool may not be able to be certified. It could be a number of reasons. It could be that there's not a standard for that. It could be that they simply don't have the ability to do that. So there are a number of factors that could come into play when looking at that. Most likely, it could be the standard, that there's not a certain standard that is applicable, but there is testing that is done to prove that it is, but it just can't be certified.
All right, Dave. Another question we had was, for a fastener that's already been seated and torqued, is there a tool to analyze the actual applied torque to get it seated?
So if we want to do any type of after the fastening type of auditing, that can be done through the use of a digital wrench that may have an auditing feature that you can use to measure at a certain degree of rotation by adding additional torque to, or you moving that fastener in the operating or tightening direction just a few degrees. You just want to get to anywhere from 3 to 10 degrees of movement and measure what that torque is. Because typically when you are measuring a fastener that's already been tightened, you do have to overcome the threshold of movement, which typically is higher in frictional forces. To get something unstuck and then have it moving again, it's going to be a little bit less. You could also use a torque analyzer with a rotary sensor. Again, this gives you the ability to measure what's happening dynamically. You could do it with the use of a dial wrench. Basically, you could mark the part and the fastener and break those lines apart in the loosening direction, and then bring those lines back together and see what that value is. Now that value is going to give you a correlational value to what the actual torque might be. It's not going to be as exact as when it was applied. And you can use a rotary sensor to do that, to see what it is when it's applied. You can then use that same setup to see what it is during that breakaway style test or line marking test, and see what those values are, because there's going to be there's no rotation, there's no other frictional forces that might be present during the actual application. But those are types of tests that you can do. You can do a full breakaway test where you're just measuring how much force it takes to break it away. Or you could do the first movement test where you actually move that fastener 3 to 5 degrees and measure what that value is, and that give you a good representation of where it was when it was installed.
All right, Dave. Last question we have is: once a fastener or bolt's been tightened and it's been, say, removed, can it be reused for another tightening application, or should it be discarded with the new fastener used?
Typically, you could reuse it if you haven't moved past the yield point, as we talked about at the beginning of the presentation. Again, most fasteners are going to have a proof load that is going to determine how much tensile strength it has. And if you go past the yield point, then that fastener is basically not providing any type of tensional forces to hold your components together correctly. So typically you'll see this in the automotive industry, especially if you're doing any type of engine work, or they'll have bolts that are yield bolts that basically we're taking them to a certain torque value and then we're turning them. And those you don't want to go ahead and reuse, or there could be a number of different scenarios where you wouldn't want to use it. But in theory, as long as you're not past the yield point of the fastener, then it should return back to its normal elastic regional range. Then you should be okay to reuse that. But again, it's going to depend if you move close to that yield point, and so on. So.
All right, that's it for today, Dave.
All right. Thank you very much for all of your questions. I hope you received some information, even if this is something that you are very familiar with. But we look forward to seeing you again next month in our next webinar. Have a great day, and we'll see you soon.